Hi friends, welcome to IGC, IIT's GATE classes. We are Bangalore-based institutes and we run basically classes for GATE, aerospace engineering, mechanical engineering, electronics, instrumentation. From this year, we have started our instrumentation engineering batches. Uh, and mostly we run the classes on weekends only, but due to this COVID-19, we have switched to online classes, right? So in today's session, we are going to see the GATE 2020 solutions for instrumentation engineering, and the subjects are sensors and industrial instrumentation. So this sensors and industrial instrumentation, this is the core subject from GATE instrumentation point of view. So before going to that, we have to first see the syllabus. I hope you people have gone through the syllabus, or many of you might have attended the previous GATE. So the syllabus starts with all the basic sensors like resistive, capacitive, inductive, piezoelectric, Hall effect sensors and their signal conditioning circuit. So this signal conditioning circuit, this is very important from sensor point of view. Next, we are having the various applications, like when we are going for the measurement of displacement, we can measure using LVDT sensors, and velocity sensors are also there, acceleration sensors, force, torque, pressure sensors. Here low pressure sensors is much more important. From the flow, every year uh, the questions used to come, especially from electromagnetic and ultrasonic turbine flow meter. So these sensors are very important. Next, we are having the temperature sensors. Here we are having many sensors like thermocouple, RTD, pyrometer, thermistor. So here thermocouple is much more important. Then in RTD we are having 3-wire, 4-wire RTD. Then liquid level, pH, conductivity, viscosity measurement. So these are, so from this year they have introduced 4 to 20 milliampere 2-wire transmitter. So this part are common for your process control as well as your sensors and industrial instrumentation, right? Okay, so here goes the first question. The first question is from the capacitive sensors. So if you see the syllabus, we are having the capacitive sensors and their signal conditioning circuit. So here if you see the capacitive sensors is here, this is going to be my sensor, and here some sort of signal conditioning circuit is there. In signal conditioning circuit of any capacitive sensors, we used to have our Wheatstone based and amplifier as well, right? So let's attend the question. The capacitance Cx of a capacitive type sensors is 1000 x picofarad, right? So this capacitance they have given as Cx is 1000 x picofarad. So we know that this sensor will sense any physical quantity, and it will provide the output in terms of change in capacitance. This is the definition of my sensor. The sensor, it will sense the physical quantity, and it will provide the output that will depend on some way to the measuring variable, that is the physical parameter. So here if you see this capacitive sensor, it is providing the output in terms of change in capacitance, and this capacitance is given by Cx and it's a function of x. So if you see here, x is the input to the sensor. So what is my physical quantity? My physical quantity is going to be x. So x could be anything like displacement, it could be anything. So in capacitive sensors, basically we can the basic formula C equal to A epsilon upon D, where A is the overlapping area, D is the distance between the plate, right? So we can change the capacitance by either changing the overlapping area or by changing the distance between the plate, or we can change even the dielectric medium also. So this dielectric medium, this mainly applications we will find in our um, level sensors, where we are having the two cylindrical plates, right? There we used to find that applications. So this is the basic introduction of about capacitive sensors. And now when it comes to solving the question, this capacitance Cx they have given as 100x. So x is the input. As shown in the figure, the sensor is excited by a voltage of 10 sine 100 pi t. So this is the supply. The other terminal is tied to the input of the high input impedance amplifier. So these things you will find many where, like high input impedance amplifier. Why? Because we don't want to take any chance of the loading effect, right? So if the first circuit is loading the second circuit, then this effect is known as loading effect. It means that this circuit is drawing some current from the previous circuit. So whatever the final measurement will be there, it will be impacted. You are not going to get the correct measurement results, right? So for that, what we wanted, we want this input impedance to be high. So the the basic amplifier that we use in our electronics is going to be our operational amplifier. So if you see that internal circuitry, then some input resistance is there, and then we are having the open loop gain. This is going to be AOL into VID. So you will find the differential voltage here, and then you are going to get V naught. So our main motto here is that we don't want to take the chance of any loading effect. So whatever the circuit is here, this circuit should not load this part. It means that if this input impedance is infinite, then this then there won't be any current that is moving from here to there, right? So this is the fundamental of loading effect. Now if you go to the actual question, so CX, this is the AG question. So CX they have given as 1000 x picofarad, and input is here, and shielded cable. So if you're going to model this shielded cable, then it would be something like your capacitance, right? So this will also offer a capacitance between this wire and the ground. So if you draw the equivalent circuit, so this is going to be my CX as usual. Here is my supply, that is 10 sine 100 pi t, 10 sine 100 pi t volts. Then we are having the shielded cable. So if you're going to model the shielded cable, it would be something like this. So here we are having a capacitance between this wire and the ground. So let it be C of cable, and then we are having the high input impedance amplifier. So just I showed you like how we are going to model high input impedance amplifier. We are having the infinite input impedance, and then we are having the output voltage from here. So this is going to be my output. So just we have to multiply with again, because there is no loading here. So next, the other terminal is tied to the input impedance amplifier through the shielded cable. The cable capacitance is 100 picofarad. So this C of cable is 100 picofarad. This is going to be 100 picofarad. Next we are having the peak of the voltage VA at the input of the amplifier. It means that they are asking about what is the input here, right? This is the peak input they are asking, right? So this is the peak value they are asking. What is the peak value when the displacement, when the x is zero point 0.1? So if x is 0.1, Cx is 1000 into 0.1 picofarad. So this is the basic question. So yeah, and so in order to find the voltage here, VID, that we have just discussed, AOL into VID. So the AOL they have not given, so we can assume it as 1. Then VID we have to find. So how we are going to find the VID? Just we have to apply the voltage division between these two capacitances. So this VID is going to be the supply voltage 10 sine 100 pi t into, we have to distribute our voltages between these two impedances. So the impedance is here is 1 by j omega, and this is going to be C of cable. Then we are having 1 by j omega C of cable plus 1 by j omega C of x. So just substitute all those values. This is going to be 10 sine 100 pi t into, so if you're going to take the LCM of all these things, then Cx will come up. So Cx upon Cx plus C of cable. So this Cx comes out to be 100 picofarad. So just substitute all those values. You're going to get 5 volt as the peak. So this will be something like sinusoidal voltage of having 5 sine 100 pi t. So this will be the peak value of 5 volts. Right. So this is the one of the easy question. This is the 1 marks question from the gate, from the sensor of. Then if you move to the next question, so the next question is from the Hall sensor. Next question is from the Hall sensor. So the question is, if I is the current flowing through the Hall sensor and B is the magnetic flux density perpendicular to the direction of current in the plane of Hall effect sensor, then Hall voltage generated is. So this is some sort of our theoretical question. So we have to know the basics of Hall sensor, how it is working, and if you know the basics, then only this question could be attempted, right? So let me quickly cover a few basics of Hall sensor. So Hall sensor basically we are using for the proximity sensor. So this is something proximity sensor, and the its structure is something like, let's say you are taking a conductor or semiconductor, and so I'm taking it at a cubical format. So if I'm taking a conductor or semiconductor and I'm passing a current I through the conductor, so if I'm passing the current I through the conductor, then what will happen, if you are placing it inside a perpendicular magnetic field, let's say the perpendicular magnetic field is here, right? So from the Hall effect, there is a one principle that we call as Hall effect. So what he told, if you are having a conductor or semiconductor, and if you are passing a current I through it, and if you are placing the conductor in perpendicular magnetic field, then voltage will be developed on the surface of the conductor, and this voltage will be perpendicular to both current as well as your applied magnetic field. So if you are seeing here, the current direction is here, and magnetic field is inside your laptop, like it's inside the copy, right? So the voltage will be induced perpendicular to both. So the voltage will be induced on the opposite faces. So this is the basic of Hall sensor. So you are going to get your VH, and it will be proportional to the current, it will be proportional to the magnetic field, and it will be inversely proportional to the thickness, right? This is going to be T. So if you see here, the Hall voltage generated is directly proportional to I. Yes, it's correct. Inversely proportional to B, no. So the option A is not correct. Then the question is, it is directly proportional to both I and B. Yeah, so the option B seems to be correct, right? And okay, so this is how we have solved this question. So this is 1 mark easy question. Next we will move to the next question. Okay, so here goes a big question, but it's not that much tough. So this question is from the strain gauge, and strain gauge basically we are using for the basics of force measurement. So if you apply the strain to any metal, so let's say I'm taking a metal wire. So if you're going to apply the force, so force could be what? Force could be in, you can apply the force either compressive, or you can apply the force as tensile. So if you're this case of compressive, and this case of tensile. So if you are taking a metal, and if you are applying the force compressive or tensile, then there will be change in the dimension. It means that now, so initially we are having the conductor like this. If you are going to apply the compressive force, then it will compress. So if it will compress, then area will be increased and length will be decreased. So this area is increased and length is decreased. So it means that there is some change in the dimension. So some change in the dimension. So due to this change in the dimension, we used to generally quantify as epsilon, and due to this change, your resistance is going to change. Resistance will change. So what is the initial resistance? R equal to rho L upon A. So now the resistance will change to some value, that is R dash, right? So then we will calculate what is the change in the resistance delta R, and this because of your change in the strain, and this change in the strain happened because of the application of the force. So let us solve this question. Let me raise this. A metallic strain gauge of resistance Rx with a gauge factor of 2. So the for this strain gauge, the gauge factor they have given as gauge factor of 2 is bonded to a structural metal with a modulus of elasticity 200 giganewton per meter square. So it is bonded to a structure made of metal. It means that strain gauge is bonded to a metal. So generally we used to, let's say this is my cantilever. So on this cantilever we used to bond our strain gauge. So let's say we are having the strain gauge like this. So we used to bond to any cantilever, and then if you're going to apply the force to the cantilever, if you're going to apply the force to the cantilever, then this cantilever will bend. So the cantilever will change its position and it will come here. So due to this, the strain that was bonded here, the sensor that was bonded here, there will be certain strain produced here. Strain will be produced means dimension will be changed. So because of this change in the dimension or change in the strain, your resistance is going to change. So if we know, if we are able to calibrate this change in resistance to the applied force, then we can find how much the force we have applied, right? So it is bonded to a structure made of metal with a modulus of elasticity as 200 giganewton per meter square. So we are having the modulus of elasticity E as 200 giganewton per meter square. So what is the modulus of elasticity? It is going to be stress upon change in the dimension. So this would be F upon A upon delta L upon L, right? So you can quantify it as epsilon. So your F is going to be, so we are not going to find here F. Let's read the question. Then the value of Rx is 1 kilo ohm when no stress is applied. So as I told, this is the first case, this is going to be second case. So in the first case, when you're not applying any force, F is 0. So at that time, what is going to be the resistance? So the resistance is going to be 1 kilo ohm. Next, this Rx is a part of quarter base with 3 identical fixed resistance and 1 kilo ohm each. As I told here, this resistance should be converted to some meaningful quantity, that is voltage or current, such that we can calibrate our output voltage in terms of change in the force or change in the strain. So we have to connect this strain gauge to the Wheatstone bridge. So this Wheatstone bridge is in quarter bridge format. It means that there is only one sensor and all the resistances are fixed. So here we are having the supply voltage. This is going to be ground, and we would be taking the output voltage from here, VOB. So let's take the fixed resistance as R, and this is going to be the sensor Rx. So the question is, if F equal to 0 means no force is applied, then Rx is going to be R, right? So this bridge is excited by 4 volts, so Vs is going to be 4 volt. The structure is subjected to a strain of 100 meganewton per meter square. So now you are going to apply the force, but here they have not given directly force. They are mentioning in terms of stress. It means that this part they are mentioning. So they are applying 100 mega newton per meter square, and epsilon is this Young's modulus is going to be 200 giganewton per meter square. So we can from there we can easily find our what is the change in the dimension. So epsilon L we can find as 100 into 10 to the power 6 upon 200 into 10 to the power 9. So this is going to be the epsilon. Now from the gauge factor we know what is going to be the gauge factor. It is going to be initial resistance. So initial resistance was Rx, and Rx was R when no force was applied. Rx into gauge factor into epsilon. So if you're going to calculate this, then just we have to substitute these values here. So what is going to be the output voltage V naught? So VOB for quarter bridge is Vs by 4 into delta R upon R. So Vs by 4 into gauge factor into epsilon. How delta R by R is going to be gauge factor upon epsilon? So it will come from here, from this equation. Gauge factor equal to Rx into gauge factor into epsilon. From here you are going to get this equation. So if you're going to substitute this would be 10. So supply voltage is 4 upon 4 into gauge factor is 2, and epsilon you can calculate 100 into 10 to the power 6 upon 200 into 10 to the power 9. So if you are going to calculate this, you are going to get 1 millivolt. This 10 to the power minus 3 will go up and you are going to get 1 millivolt. So this is 2 marks question from the strain gauge, and this is not a tough question. This is some sort of lengthy question. Okay. So next we are having the question. So this question is from piezoelectric sensor. So this question is from the piezoelectric sensor. So this piezoelectric sensor basically it is used for the measurement of force, displacement, like that. So let me briefly introduce about the piezoelectric sensor. So this piezoelectric sensor, it is made up of a piezoelectric crystal, and it works on the principle of piezoelectric effect. So what is piezoelectric effect? If you are going to apply the force to any piezoelectric crystal, so this is going to be piezoelectric crystal, and this could be synthetic, natural, or even polarized also, right? So if you're going to apply the force to the piezoelectric crystal, then change in dimension will happen. Change in dimension. So let's say if the thickness was t, now it will decrease to, this will be, it will be reduced by delta t. So now what is the final thickness? So t dash is going to be t minus delta t. So if you are going to apply the force, then displacement will happen, so delta t. Due to this displacement, due to, with the help of polarization, the positive charges are going to be acquired at the upper surface and negative charges are going to be acquired at the lower surface. So with the help of polarization, positive charges will be acquired at the upper part and the negative charges are going to be acquired at the lower part. So how we are going to collect the charges? Just we have to put the two electrodes. So we can put two electrodes here, one on the upper surface and another on the lower surface, and then we can tap out the charges and then we can store these things, right? So this polarization, how this is happening, basically if you take the example of piezoelectric crystal, let's say SiO2. So in SiO2, how the bonding is happening? So it would be oxygen is here, then we are having oxygen here. So these are attached here, covalent bonds are here. Now if you're going to apply the force, then this will break. So this will break and then silicon will acquire here positive charges and oxygen will acquire the negative charges. So due to this, I'm saying that the positive charges will be accumulated at the upper surface and negative charges are going to be accumulated at the lower surface. So this effect we basically call as polarization, right? And so this was the basics of my piezoelectric sensor. So what I told here, if you're going to apply the force, then displacement or deformation will happen. This deformation will lead to development of charges, positive charges and negative charges, and this we can store and we can get the output voltage here. So from any capacitance, how you're going to get the output voltage? Q is equal to C into V. So V equal to Q upon C. So V equal to Q upon C. So whatever the charges that you are going to get here, you can divide it by capacitance, then it is going to be Q upon C. How capacitance is getting formed? These two electrodes are there and in between piezoelectric crystal is there. So this is going to be working as the dielectric. So I can say that this is going to be the piezoelectric crystal that is attached between the two electrodes, right? So how force and this deformation is related? So this is related with the constant, and that constant we used to call as E, modulus of elasticity. So this will be force upon strain upon change in thickness upon thickness, delta T upon T, right? And how force and charges are related, how force and Q is related? So this is related with a constant that we call as D constant. So Q equal to D upon F. So if you are able to find Q, and then you can substitute Q here, and C is nothing but A epsilon upon D. A epsilon upon D. So this is the basics of my piezoelectric sensor. Yes, piezoelectric sensor. And let's read the question. What is there? So supply voltage is 5 volt. So this op-amp is powered with the supply voltage of 5 volt, and sensor is attached here. This is going to be sensor. So we are going to model the sensor, and then you will find that these two will constitute the sensor. These two parts. So this we call as charge generator, and this we call as capacitance of the piezoelectric sensor. So these two are the part of piezoelectric sensor. Then we are having the cable capacitance, that is the 100 picofarad, and then the feedback capacitance is connected as 100 nanofarad. So here the concept of charge amplifier and all these things are coming. So I'm not going to cover those things because the otherwise the video could be very lengthy. So hope you have gone through the charge amplifier, how it is working, and what are the demerits with the normal piezoelectric sensor, why we are going for the charge amplifier. So let's try to solve this question. So if you see here, this negative supply is given as 2.5 volt. This positive, let me erase something. So this negative supply is 2.5 volt and positive supply is, so this is going to be 2.5 volt. And if you see here from the virtual ground concept, you can see whatever the voltage that is here, it will be directly appear to the negative terminal. So this will be also 2.5 volt. If this is 2.5 volt, this will be also 2.5 volt. So will there be any current flowing through this piezoelectric capacitor or your cable capacitance? No. So there won't be any current. It means that whatever the current that is generated from the this charge generator, it will directly go to the feedback capacitance and it will directly appear here. So the question is if the charge QP generated by the piezoelectric crystal is of the form, so this is, they have given as QP as a function of t as 0.1 sine 10 to the power 4 pi t microcoulomb. The peak detector outputs after 10 cycle of QP. So this is some sort of sine wave. So after the 10 cycles have passed, what is going to be the output? So if this is something like a 10 peaks, so they are asking about after 10th peak, what is going to be the peak. This is the peak detector circuit, electronic circuit, so it will find what is the peak voltage here, right? So we have to find that. So first you have to calculate the current. Then this current will pass through the capacitance, then you're going to get your output voltage, and from there we can find the peak value. So what is going to be I of t? So I of t is nothing but dq upon dt, right? You can find it. So iq of t, so iq, let me check the pen. Okay, so iq of t is nothing but my dq upon dt. So iq of t is dq upon dt. So from here we can find the current, and if this current passes through the capacitance, then we are going to get your final output voltage, that is vp of t. So from there we can find the peak value, right? So let me focus on this part. So I'm going to erase this here. So we are having the capacitance here. Let me change the color. This is going to be green. So see here, we are having the 100 nanofarad capacitance here, and then we are having the 2.5 volt here, and here we have to find the what is the value of vp of t. So what is the value of vp of t? If iq of t is the current passing through it, so we are having 2.5 volts, and then we can minus vp of t, then we are going to get your the voltage that is here, that is drop, the voltage drop across the 100 nanofarad capacitor. So what it could be? It could be q upon c. So 2.5 minus vp of t equal to qp upon c. So qp they have given as 0.1 sine 10 to the power 4 pi t. This is in the microcoulomb, so we can multiply with 10 to the power minus 6 upon c. So c they have given as 100 nanofarad, so 100 into 10 to the power minus 9. This is going to be 2.5 volt minus vp of t. So if you're going to solve this, you will find that vp of t is going to be 2.5 minus sine 10 to the power 4 pi t volts. So if you're going to plot this 2.5 minus sine 10 to the power 4 10 to the power 4 pi t, it means that this is some sort of clamping where your sine wave is oscillating about 2.5 volt. 2.5 volt. So your sine wave is oscillating about here. So what is the peak value here? If this is the magnitude as 1 and minus 1. So this is going to be 2.5 plus 1. This is going to be 3.5 volt. Right. So this is one of the good quality question from the piezoelectric sensor. And so this is how we have seen questions from the instrumentation engineering. And these are not the tough questions. These questions could be attempted if you are going through the concepts, right? So if you see here, the questions are mainly from capacitive sensors, inductive, piezoelectric, and flow sensors are very important. So if you are appearing for the gate instrumentation engineering, then from sensor point of view, what I would suggest you to cover, you have to be very thorough from the flow sensors. Though this year they have not asked the questions, but the questions are expected from the flow sensors. Here you are expected to cover at least turbine flow meter, electromagnetic flow meter, and ultrasonic flow meter. So these three sensors are important. From temperature point of view, you have to cover the thermocouple. Thermocouple is very important. Then you can cover strain gauge, you can cover capacitive sensors, you can cover LVDT, right? So these things are very important from gate instrumentation point of view. And apart from that, everything is important, but the scoring part are here. From the turbine flow meter, electromagnetic, ultrasonic, every year 2 marks questions or 3 marks question used to come from this topic, right? Okay, so we can stop here. Then if you are having any doubt, then you can mail to iitiansgateclasses for any sort of doubts, right? Thank you.